Hi class! Today we're starting on chapter 1. At the end of this chapter we should be learning how to do differentiation, but before we can do that we want to start off with a concept of limits. So this section is all about limits. We're going to look at it with a numerical and a graphical approach. One thing we want to do is whenever we have new notation, we want to learn how to say it properly. So let's look at this notation. This new notation says limit as LIM, and under that you write as x approaches a with an arrow, and then to the right of it you put the function that you're talking about. We would read this out loud as the limit of f of x as x approaches a. And then we have over on the right hand side that it's equal to some value L. It's also important to understand that you can have a left hand limit and also a right hand limit. Well, what does this mean? It means that you can have a limit as you approach a number from the left side or from the negative side, or you can have a limit as it approaches a number from the right side or the positive side. These are signified by the plus or the minus sign on the upper right hand corner of the number that you're approaching. Let's take a look at that. For our first example, we want to look at the sequence and determine its limit. That is, we want to figure out what number are we arriving at the very end of the sequence if we went on for infinity. And we start off with 0.3, then 0.33, then 0.333, and we continue adding on 3's at the end of our number, and I think we're headed towards 0.3 repeating, which would be 0.33333 all the way to infinity. But the question is, how are we arriving at that? Are we arriving at 0.3 repeating from the left-hand side or the right-hand side? Well, when we think about this number on a number line, if you think about the progress of the numbers, it starts off at 0.3 and it ends up at 0.3 repeating. And so we're coming at it from the left-hand side. And so we could write this as x approaches 0.3 repeating from the left-hand side, and we use the minus sign to show that it's coming from the left-hand side. For our next example, we start off at 4.1 and then go 4.01, 4.001, 4.0001, and it keeps on going and going, and we think we would approach the number 4. So let's think about that on a number line. In the grand scheme of things, going from 4.1 and the numbers are getting smaller and smaller, and we end up at 4, we're approaching the 4 from the right hand side. So we would say that x approaches 4 from the right hand side, using a plus symbol to symbolize that we're approaching it from that side. For any graph, it doesn't matter if our number is positive or negative. It just matters if we're approaching it from the positive side or from the negative side. So the left-hand side is the negative, the right-hand side is the positive. Now I want to go back to this theorem, because when we're trying to find limits, it's really important to know that you have to know the limit as it approaches the value from the left, and also the limit as it approaches the value from the right. So we want to check both of those, and if the right-hand limit exists and the left-hand limit exists, then we know that the whole limit exists. And so to be able to check if a limit exists, we're going to check it coming from both sides. Let's apply that theorem to question number 2. What we want to find is the limit of f of x as x approaches 3. But first, to do that, we want to find it as it approaches from the left-hand side and from the right-hand side. To do the left-hand side, we want to approach the 3 from numbers that are less than 3. That is, let's start at 2 and get closer and closer to 3. I plugged in the values for x using my calculator, and I can see that as x approaches 3 from the left-hand side, then the f of x approaches the value of 1.5. Let's go ahead and do this from the right-hand side. Once again, I plugged in the values of x approaching 3 from the right-hand side, and I found the values of f of x approaching 1.5 as well. So because the limit of f of x as x approaches 3 from the left-hand side is 1.5, and the limit of f of x as x approaches 3 from the right-hand side is also 1.5, then the limit of f of x as x approaches 3 is 1.5. We need the left-hand side and the right-hand side to exist and agree with each other for the regular limit to exist. To do video example 3, I want to start off by finding f of 4. And f of 4 we get by plugging that value in, so I get 16 minus 16 over 4 minus 4. And notice that you get 0 over 0. We call that indeterminate. And a lot of times when a value is indeterminate, we can still find the limit as x approaches 4, but we can't actually find f of 4 itself. So that's why we want to find a limit, because when we plug 4 into this function, it comes up with this answer that we don't understand. So I plugged this function into my calculator, and for the values of x approaching 4 from the left-hand side, I get the following answers: 7, 7.5, 7.9, 7.99, and 7.999. Therefore, it looks like the values of f of x approach 8 as x approaches 4 from the negative side. So my limit would be 8. Plugging in the values of x approaching 4 from the right-hand side, then my f of x becomes 9, 8.5, 8.1, 8.01, and 8.001. So you notice that the limit of f of x as x approaches 4 from the right-hand side is also 8. So does the left limit agree with the right limit? If the answer is yes, then the limit of f of x as x approaches 4 is going to be 8, since they match. And we can write it in this way. You want to read it out loud as this statement, even though the notation says this. And you have to get practice at writing that notation. Video example 4 asks us to graph the piecewise function k, which is broken down into two equations, and the domains are separated by the number 3. So we have the domain going from negative infinity to 3, and then from 3 to positive infinity. Let's draw that boundary line first. And then let's just plug in the numbers that are less than or equal to 3. And then let's just draw that line. Alright, and then let's go ahead and plug in the numbers on the other side of that boundary line. Notice that I don't say f of 3 again because there's only one f of 3, and that was the first equation, but I do want to plug 3 into that second equation to find out where to put my open circle. And then the rest of the points we'll go ahead and get graphed. Now you should be able to see that the limit of the blue graph when I'm approaching 3 is going to be this value 1. But the limit of the dark blue graph as I'm approaching 3 is negative 1. And it depends on which side you're coming from. If you're coming from the left side or if you're coming from the right side. So our answer might be different approaching from the left as approaching from the right. Let's go see what that looks like when we do it algebraically. Let's use our graphing calculator to help us solve this. And we're going to plug in these values into our k function. So k of 2 is 2, k of 2.5 is 1.5, and then we get 1.1, 1.01, and 1.001. And so the limit of this function as x approaches 3 from the left is 1. Approaching from the right, we're going to get k of 4 is 1, k of 3.5 is 0, we get negative 0.8, negative 0.98, and negative 0.998. And so the limit of k of x as x approaches 3 from the right is negative 1. And then we see that the left-hand limit exists, and the right-hand limit exists, but they don't agree. And since they don't agree, then the limit does not exist. And it's important to use that wording. You can't say no solution or zero or not anything like that. You have to use the wording, the limit does not exist. Let's do this again with the limit of k of x as x approaches negative 3. When we plug in the numbers coming from the left, we get 8, 7.5, 7.2, 7.1, and 7.01. So the limit of k of x as x approaches negative 3 from the left is 7. Plugging in numbers headed towards negative 3 from the right, we would get k of x is 6, 6.5, 6.8, 6.9, and 6.99. So the limit of k of x as x approaches negative 3 from the right-hand side is also 7. So if we ask, does the limit agree from the left and the right? Yes, both of these approach 7. Therefore, the limit of k of x as x approaches negative 3 is 7 overall. As an alternative to the numerical approach, as we saw in our last example, we could also look at this graphically. So if I want to find the limit as x approaches 1, I draw a vertical line at x is equal to 1. And then I can look at the values as the graph approaches that from either side. So as I approach 1 from the left side, h of x approaches 4. And as I approach x from the right side, h of x is equal to negative 2. And you see that those limits are not the same. One approaches 4 from one side, and one approaches negative 2 from the other. So we would say this limit does not exist. Easy to see graphically. But for our next example, as we ask for x approaching negative 3, then we want to look where that's going. And from the left side, we see that h of x approaches negative 4, and on the right side, it also approaches negative 4. It approaches the same number from the left and from the right, so therefore the limit of this function is negative 4. Let's use this graphical method to find the limit as x approaches 2. So when we ask ourselves what is f of 2, notice that there's an open circle on this graph. F of 2 does not exist. It's not defined in this function. However, if we look at the limit as it approaches 2 from the left-hand side, we notice that it's approaching 3. If we look at the limit from the right-hand side, we notice that it is also approaching 3. Therefore, the limit of f of x as x approaches 2 is also 3, since the limit exists and it matches. Even though f of 2 does not exist, the limit of it exists. And the limit of f of x as x approaches 2 is 3. That way, we can find values that do not exist as part of the function, but still we can figure out where it's headed as we get close to that value. For video example 6, they ask us to consider the function f of x is equal to 1 over x minus 2 plus 3. And they ask us to graph the function. So I went ahead and used desmos.com to help me figure out what the graph should look like. And I found that it has an asymptote. It has two asymptotes, one vertical and one horizontal. And our equations for our asymptote should be equations for lines. So x equals 2 and y equals 3. And then we put our values of our graph in. So there's the graph of it, and I've labeled some important values on the x and the y axis, and I've labeled my asymptotes. And when we ask ourselves, what is the limit of f of x as x approaches 3, we look at 3, and f of 3 exists. It's this value here. But you notice that going from the left-hand side, we're approaching that value, and going from the right-hand side, we're approaching that same value. So that answer would be 4. When we ask ourselves, what is the limit of f of x as x approaches 2, Well, when we look at 2, we have an asymptote here. And when I'm approaching 2 from the left-hand side, the value approaches negative infinity. And as I'm approaching 2 from the right-hand side, the value reaches positive infinity. And those aren't the same answer, so that does not exist. And then we have the limit as f of x approaches infinity. And notice that you can only approach infinity from the left-hand side. So as I approach infinity, I'm going that direction. And I notice that the value is getting closer and closer to a 3. The y value is getting closer to a 3. So the limit is 3. So we can also find the limit numerically as we approach infinity from the left-hand side. I put this in my calculator and I get 3.33, 3.125, 3.0102, and 3.001. And you can see that the numbers are approaching the value of 3. So does this match what we observe on the graph? Yeah, we observe that it goes towards 3. And so numerically and graphically, we found the limit as x approaches infinity as 3. For video example 7, we're given the function h of x is equal to 1 over 1 minus x plus 6. And so we're asked to find the following limits. Now notice that the first limit is as x approaches 1. But if I asked myself what is h of 1, h of 1 does not exist because that would make that denominator 0. So we do have to find the limit the normal way. Let's look at the second one. Notice that h of 2 is equal to 5. And because I was able to find the value of the rational function, the limit and the value of h of 2 will be the same. And so I could say that the limit here is 5. We're going to check our work graphically. But anytime I can do this with a rational or a polynomial function, if I can find the value of that function, then it's going to match the same as the limit. The rest of these, I can't plug in 1, I can't plug in infinity, I can't plug in negative infinity. So we're going to have to find those limits a different way. Let's look at the graph real quick. And looking at the graph on Desmos.com really gives us a picture of what's going on here. At these values, as x approaches 1, there is an asymptote. So let's look at what happens. We have the value going to positive infinity as it approaches 1 from the left-hand side, and the value of the graph goes to negative infinity as we approach 1 from the right-hand side. So because 1 goes to positive infinity and 1 goes to negative infinity, that limit does not exist. Now in this case, we have the limit does not exist as well as the function did not exist at 1, but that's not always true. Sometimes we'll have that h of 1 does not exist, but we can still find the limit if we can find where that graph is headed on both sides. Now for this next one, for C, we can't find h of infinity. That's not even a thing. We can't plug infinity into anything. So we just have to look at the graph and figure out where is this asymptote or where is this graph going when it approaches infinity. And you can see that as it goes towards positive infinity, the graph value is approaching 6 on the y-axis. And then also, as it's approaching negative infinity, it's also going towards 6 on the y-axis. So that's going to be my limit for both of the next answers. So the limit as x approaches infinity is 6, and the limit as x approaches negative infinity is also 6. That's a lot to take in for this section, so let's just review some of the rules. To review this section, we want to talk about the notation, writing the limit of f of x as x approaches a under the word limit, and then knowing that we have left-hand limits coming from the negative side and right-hand limits coming from the positive side. If my left-hand limit and my right-hand limits are not equal, then the limit does not exist. However, if they are equal, then the limit does exist and the limit matches them. A limit may exist even though a function value does not. If we plug in a number into a function, we might not get a value, and that might not exist, but we can still find the limit as it approaches that number. And also, the limit may exist and be different from that function value. So even if we plug a number in, it might be different. However, we did learn that if I have a rational function a polynomial, or any other type of function like that, when we plug in a number into that function, the limit will match, and the limit will exist and be exactly the same if we solve it. So that is one exception to this rule. All right, get some practice in. It's just through working with these that the limits will start making sense as you get that practical practice. Thank you and have a good day.